Thanks very much, Mike, and to all of you for coming along today. Just get up to date with the technology. My title of my talk is Gravity for Hydrocarbon Exploration, a new look at an established tool. My extract makes the point that the first hydrocarbon discovery was, or geophysical discovery, was through gravity, and we're now very much a smaller part of the industry to seismic. But we like to think that we can add value in certain sectors, and I'm going to be talking a little bit about that today. Wallace Pratt said it fairly eloquently about oil being found in the minds of men and women, as we've just heard. I have the great privilege of working with Dr. Reid, who some of you may know is a well-known figure in gravity and mag work here in the UK and internationally. He puts it a bit more bluntly. And he says this to me from time to time: work with your brain in gear. We're constantly confronted with new technology, improving technology, but actually, we, the people in this audience, some of us have been here for a lot of years, some for not so many. Our primary asset is our ability to think straight. And whether oil is at 120 or whether it's down at 35, that's still a valuable commodity, in my opinion. So I'm going to be giving you just a quick run through of kind of Gravity 101, some basics. I will put a few formulae up on screen, but it'll only be a few. Obviously, we're here talking today about hydrocarbon. Some of the instruments I'm showing you today can be used for finding mine workings within 5 meters of surface. The very same instruments, we can be prospecting for hydrocarbons down to 4, 5, 6 kilometers. And there's plenty of applications. I'll give you a bit of a whirlwind through some of those. There are some important comparisons. I have a couple of soapboxes, but I think they're not just soapboxes of my own, but ones that bear repeating to this audience. And I'll come to those in a little bit of detail. And then recent developments, hopefully for those of you who've been in the game for a bit longer, as with seismic, as with spectral decomposition, as with so many of the techniques we've heard about today already, gravity keeps reinventing itself. We can't beat physics. We have to work with the physics, but sometimes there are better ways of exploiting what the physics is telling us, so that we can do our job as explorers. All right, Newton's law of universal gravitation says roughly that if you've got two masses, they're attracted to each other with a force that's proportional to the product of the masses and inversely proportional to the square of the distance of separation. So that's all very nice and very useful, because otherwise we'd be floating somewhere around the auditorium rather than sitting where we were on our seats. Newton's second law of motion says that if you've got the force experienced, or a mass experiences a force that's proportional to the acceleration. If we combine those two, then we get that for any point mass, and that can literally be a ballpoint pen or a petroleum basin at depth, the magnitude of the acceleration due to gravity on Earth is directly proportional to the mass of the Earth, inversely proportional to the square of the Earth's radius. So that tells us quite a few things, and if this was a 3-day workshop, I'd go into all of those in some detail. You'll be relieved that it's not a 3-day workshop, and I'm not going to go into them in detail. But what it tells me is that it matters where we are in relation to the mass that we're trying to measure. So these things make an important difference. Gravity varies from place to place because of the Earth's shape and rotation, because of the surface topography. When we get down to the details with gravity surveys and whether those are ground or airborne, we spend a lot of time measuring the topography, the topography of the ground, and particularly because that's close to the measurement source. We're on the surface of the ground, or we're up in the air, or what have you. It makes a lot of difference. Sometimes the features, the structures we're looking to image are orders of magnitude deeper than the effect of the surface topography, so we've got to get that right. And variable mass distribution, well, yeah, that's only one of 4 variables, but that's actually what we're all about, because if the Earth had no variable mass, then density, gravity as a tool would not be useful to us. So two broad families really of gravity instrument. A gravimeter or gravimeter measures the vertical acceleration due to gravity. If I drop this remote, it'll fall to the floor, and that'll happen at a certain acceleration, and we know this from first year physics perhaps. The units there are the SI units, meters per second squared, obviously acceleration. In our gravity universe, we tend to talk about something called a milligauss. And a milligauss is 10 to the minus 5 meters per second squared. These are the terms you'll see in the literature, which is why I cover them briefly and for your reference if you look back on this recording in due course. The Earth's gravity is about 1 million of these things called milligauss, and modern instruments can measure to about 0.01. So, we've got however many orders of magnitude, 8 orders of magnitude there. What these contractors do is fairly impressive stuff. Along comes gradiometry and says, right, we're not only interested in the vertical acceleration due to gravity, but we're actually interested in its gradients. That raises a very interesting question. What do you mean by vertical? Rock masses pull measurement instruments sideways as well as vertically. And so it's all about the gradients and the way we build things called tensors, which are mathematically quite complicated, but from an exploration point of view, fairly useful. And again, we've got some terminology. The SI unit for because it's a gradient of acceleration, so you drop the meters, you just end up with the per second squared. And typically we talk about ETVOS being a measure of that gradient of acceleration. The Earth's total vertical gravity gradient is around 3,090 of those ETVOS units. And again, modern instruments can measure about 3, so 1 in 1,000th. And getting this kind of thing right is difficult. There are some clever instruments, some clever people out there. These are some of the instruments that are used. The one top left there is a ground-based instrument. Some of you may have had the dubious pleasure in your training, your university training to use the CG5, the autograv. It's a great piece of kit. It just needs a bit of love. It's misunderstood. The other ones are a bit more high octane. These are all airborne systems. The obvious point that with an airborne array you can cover a lot of ground a lot more quickly. It's also a far more hostile environment. If you've got a CG5 and you plonk it on a tripod, the Earth stays roughly where you put it, and everything certainly doesn't become straightforward, but there's not the complexity of being in a moving environment where the instrument and the aircraft are themselves accelerating, and that's playing havoc with the very, very tiny acceleration measurements that you're trying to make as an explorationist. So gravity system bottom left, they're all kind of black boxes, folk. There's some very clever electronics inside, but for the sort of photo parade, this is what the instruments look like. I'll come to each of these airborne systems. These two, I beg your pardon, let's do the other one, shall we? This is a gravity gradiometer, this is a gravity gradiometer, and that's a whole field gravimeter sitting in an aircraft. All right, some applications in hydrocarbon. There are several things that we can do to assist. Now, gravity doesn't exist in isolation any more than seismic or sequence stratigraphy or what have you exists in isolation. We need to be part of a team. We, Alan and I working as consultants, need to be in collaboration with our clients, working in their offices wherever we can. This is an example of, we'll spot the basin. It happened to have been Melanie Sub-Basin, Western Australia. This was ground gravity, actually, supported with helicopter because you can get around to difficult areas. And what happened was, this is a Bouguer gravity image, so there's been some terrain correction involved in this. And then this is I apologize, I did try to get a high resolution version of this particular image, but an inversion surface, so a depth debasement, if you will, from that image. And on this occasion, it's not hard to see the basin in the gravity image itself. Sometimes we need to tease it a bit more to actually get the topographic information at depth that we're interested in. This was one that Reid Geophysics was involved in for Remsa, Repsol in Libya a few years ago. Fairly straightforward target model. We've got a sandstone reservoir with a shale caprock seal, and so we want to know where the the reservoir is, the topo highs in the reservoir at depth. So again, some survey stats here. A fair bit of work, 6 and some thousand gravity stations over a survey area of 15,000 square kilometres. The repeat stations, the stats I won't trouble you with. But it got quite interesting. Out in the desert, we had to make surface terrain corrections to take out the effect of the sand dunes, which, as I've said before, being close to source, were a major source of noise otherwise, and close to GPS control. Getting your levels right is key in gravity. Jumping straight to the conclusion on this this occasion, what we're picking here is this is an interpreted map of possible traps where the sandstone is coming up underneath the shale cap, ergo the one's been quite preferentially concentrated, and just a marvelous example really of going directly from a density model straight to prospectivity. It doesn't always go this smoothly, but this is a neat example of gravity giving direct value to a project. We didn't make it up. There's a seismic line in sort of deep black, and second one here. Where those seismic lines cross, can you see there's an east-west elongated structural high? And that was proved by the seismic that the gravity was making sense. This is Libya, southwest Libya. There's oil seeps up to the north. We're in elephant country here. So there's every chance, and of course, sadly, the politics have gone a bit sideways. That we're not quite clear how this prospect developed, but there's every chance that the gravity was really helping on this occasion. Pre-stack depth migration is not something that I'm going to speak very much about because it's certainly not my expertise, but it's another place where gravity can be helpful in filling in some of the blanks. We know that the difficulties of imaging subsalt with seismic, and so we have a slightly cartoon version here of a pre-stack depth migration initial velocity model, supplemented then with gravity observations to produce an enhanced model. But what I want to get to is the ability using the gravity control to differentiate between, are these velocity pull-ups? I'll flick to the final result in just a moment. Are we seeing structure at depth, or are they velocity pull-ups? Let's go to the next slide. If you can just watch the 3 arrows there. And what we can see there is that no, it's not a structural pull-up. It is actually, it's not a structure in there, it's a velocity pull-up. The densities, the seismic velocities used were inappropriate. The gravity was able to constrain those, and so in that regard we're getting a tighter inter on this particular field. Subsalt imaging I've spoken about. There's a lot of work in the literature just now. On the left here is the SEAM model put out by the SEG. They made a particularly tough, tricky synthetic salt model, and a bunch of gravity practitioners have thrown their respective softwares at it to good effect. The take home is gravity is helpful at imaging through salt where velocity inversions or problems with the seismic preclude effective resolution unless you've got these very long offset lines. The one on the right is a wonderfully optimistic salt surface. I've taken it off one of the contractor websites. I'm assuming that's what the salt looks like. But again, as I've said before, gravity exists in context without tight control. You can make it be what anything that you want. I'm not suggesting that's been done on this occasion. I'm sure there's good closure and good control. There's certainly some seismic kicking through the gaps here. But do be aware of unconstrained gravity and density inversions. You need well control where possible, you need seismic control where possible, and you need a decent geologist at your elbow if you're a geophysicist doing the work. Take a little more time on this particular study. This was, some of you may know Richard Milton Wurzel from DEC and co-authors. They put this paper out about 2010, looking for carboniferous petroleum system beneath the central North Sea. They took some long offset, 2D and 3D seismic profiles and grids. Looked pretty hard at them in this area, and then introduced gravity because what they were trying to do was to to constrain the top of crystalline basement. The basic agenda was you need space within the stratigraphic column to fit a basin or basins. So it's critically important where the crystalline basement is, and sometimes that's not easy to pick off seismic. So they built that, as you'd expect, a density. They assigned densities to the various strata in the section. They created a seed model. Base Eckstein was important to them, top crystalline basement, and then they allowed, they forward modeled the top crystalline basement and then allowed it to move up and down under inversion to get some fine detail, and came up with a plot that one looks fairly impressive, but two is highly likely to be a substantial step forward on what was achievable from seismic alone. So again, the take home, one of the main things that we do is helping people to pick depth to basement using gravity, preferably in conjunction with seismic and other techniques. So there we are. This is one of the sort of the sound bites from that publication, separating the gravity response of the basement from its overlying sediments, and so that we could obtain the accommodation space that was needed to create a possible basin or to infer a basin of possible exploration interest. All right. Important comparisons. This gets a little contentious, so these views are mine, rather than necessarily what you'll always get in the literature. The first one is not particularly contentious. It's saying that we're pretty much there with airborne survey. We can now get results that are broadly comparable from airborne to what you can get from ground stations, unless, and I'm speaking with my petroleum hat on, if you're in a minerals world, you need closer station spacing, finer resolution. You won't necessarily get that from the air. But from 99 out of 100 petroleum applications, airborne is a good choice. In essence, what we're looking at, gravity from the air, gravity from the ground, very similar images. This is a test range in Australia. Gravity gradient from the air, gravity gradient on the ground. Again, broadly comparable images. I can talk more about this, obviously, to those of you who are interested. Gravity and gradiometry, there's a bit of a turf war going on. There's a lot in the literature now about the marvels of gravity gradiometry, systems like FTG, full tensor gradiometry, systems like Falcon, put out by CGG. AirFTG is in flux. One of the contractors failed about 3 months ago, and there's going to be at least 2 new operators. The established player is Bell Geospace. And FTG is, and gravity gradient is marvelous where you're looking to image shallow structure. It's not as useful if you're looking for very deep structure, because the long wavelength information is not in the measurement. You have to introduce it from other sources. Sometimes it can be more helpful to fly a gravity survey, thank you, because of the deeper information that you get and the fact that you can fly broader lines, and hence improve your costs, or reduce your costs even. Again, happy to chat more about that, but just a little flag. Gravity gradiometry is a marvelous technique. It's not directly applicable in all petroleum exploration situations. Full tensor versus partial tensor, again, getting a little esoteric here. We've got the 2 main players, being the AirFTG and the Falcon system. There are benefits to both. But it is important that in a given exploration context, you think fairly hard about things like line spacing, things like target depth, and what you're wanting to resolve. Always worth, and again, both of these contractors will do your proof of concept modeling before you pull your wallet out of your pocket, to show what they're likely to achieve on a given survey. Make sure you've got someone who knows what they're doing to be advising you in that kind of situation. Recent developments then. This is no secret. Everybody's innovating across our sector, and airborne and ground gravity are no exceptions. We reckon you can probably get double the resolution now with an airborne survey to what you could 10 years ago, just because of improvements in instrumentation, things to do with the way that surveys are flown. Sometimes instruments are helicopter hosted. Of course, you've now got a slower system, so your sampling statistics are better. You can do clever things with your noise levels. Marine gravity similarly, although oftentimes marine is on the back of a seismic survey, so the seismic vessel is going to keep going. If the gravimeter breaks, that's too bad. Maybe they'll pick it up next day or next week. So quality of marine gravity service can be patchy, but if you can control those at all, you stand to get extremely useful data with modern survey techniques. Gravity gradiometry I've spoken about. One of the pieces of news is that there's a new system coming out that's double the disk size, that previous slide. So your noise levels again are going down. More detail if you're interested. Absolute gravimetry, there's a bit of a commercial problem here where there's a marvelous instrument that would probably be built, but the particular manufacturer has a competing instrument that they don't particularly want to eclipse. So sadly we'll probably have to wait. It's been 15 odd years so far. Hey, perhaps we'll get a chance to use absolute gravimetry at one stage, by which I mean not relative measurements, but the actual value that you would get if you dropped your apple, what value of gravity would be measured at that point, to borrow an image from Newton. The MEMS gravimeter, you might have seen this in the press just recently. Tiny little thing like a postage stamp. It's going to change the world as we know it, or not. It's a little like the gravimeter we get in our mobile phones, but a lot more sensitive. This was a genuine image, and these are clever folk. I'm not taking away from Middlemiss and others. This is measuring earth tides. The earth, like the sea, expands and contracts over a 24-hour cycle, as you're probably aware. And this may well, be a really helpful technology. At the minute, it's on the lab bench, and for those of us who've been in production for a while, you know that it's a good long time and a fair bit of perspiration to get from a lab bench to a working survey environment, but an interesting technology nonetheless. This remains really, for me, the most important tool for gravity or indeed any other exploration. Several speakers before me today have made this point, but honestly, keeping a tight handle on the ability that we have as explorers to make sense of a difficult environment, both geologically and at the minute commercially. And again, to borrow from Alan, just make sure that your brain's in gear. Thank you very much.
Thanks very much, Tim. Bit of a gamble showing all those equations so soon after lunch, but I think you got away with it. One very quick question, if you've got one. Yeah, Nikki.
Can you say something about the current status of satellites? Post-grades.
Yeah, absolutely. So there's a really useful source of free, yes, you heard me right, free information. Sandwell and Smith and others publish on that. And for broad, super regional exploration, it's a wonderful source of genuinely free information. You go out and you download it off the internet. There are innovations being made in that regard by people including GTEC here in the UK, where they are more accurately picking the first arrival on those satellite data, and in that regard they're getting a better geoid and therefore more accurate measurements. That, I'm afraid, is a service that you do have to pay for. But again, people are innovating all the time. There are new missions going up. That's certainly something to look out for. And critically, at early prospect stage, it's free or close to free. So thank you.